Welcome back to another section. We are going to have control volumes now. So finally we get to have some mass flowing in and out of our systems. So that'll be good. Now this next equation, I'm just going to give you the equation. The textbooks have the derivations. I don't think we need to derive it because it's similar to the other equation. So this will be your control volume entropy rate balance equation. So essentially it'll be our entropy balance equation we use when we have mass flow. The left hand side of this equation is going to be the time rate of change of the entropy in the control volume. Note that that's a capital S right there. This is equal to the sum of Q dot and put it over T. Notice I've got this J subscript. If y'all remember from the last example, we had that temperature of the boundary given, and then the equation we used was just Q over that temperature. This sum here is just in case you have different heat transfers over boundaries that have different temperatures. So that's all this is. Now this next term is for the inlets. So for the inlets, you're going to sum up all of the inlet mass flows times the entropy at the inlets. Then you're going to subtract, this is for the exits, the sum of all the exit mass flows times the respective entropies, and then we'll have plus sigma CV dot. And we'll define what all those are in just a second. Notice there's a dot up here. This left-hand side, that is the rate of entropy change. So we've got that. The right-hand side, these first three terms, they go together. These are the rates of entropy transfer. And then finally, this last term, that is the rate of entropy production. All right, so this is going to be the equation we use when we have mass flow. So make sure if you have a closed system, you don't want to use this one. You would use the other one that we used previously. Now the only other thing we need to write down is the steady state form. The steady state form of this equation is just going to set this left hand side to 0. Everything else will be the same. So basically just copy down the right hand side. It's a dot, not a bar. And then we need our mass flows for the inlets. Then subtract the ones for the exits. And then add entropy rate. Okay, so now you have this. Now again, this is only for steady state. If it's not steady state, don't use that because you need to find that left-hand side. Okay, so let's go ahead and go into this example. This example has a lot of parts to it. We're going to have air as an ideal gas that's flowing through the turbine and heat exchanger arrangement. We've got steady state data that's given on the picture. We're going to ignore stray heat transfer and kinetic and potential energy. We need to find quite a few things. We want to find temperature T3, our power output of the second turbine, rates of entropy production at turbine 1 and heat exchanger, and then we want to rank our components in order of inefficiency. Now, key things we need to notice: ideal gas, we've got steady state data given, and we're going to ignore these three things. All right. Before we get started, let's look and see what's going on with this system. We've got air coming in at a temperature of 1400 kelvins, pressure is 20 bar. It goes through this turbine, it's going to spin those blades, power is going to be generated. That power output for this turbine is 10,000 kilowatts. Then air comes out, temperature is now reduced to 1100 kelvins, Our pressure is also reduced to 5 bar. Now we're going to send this through a heat exchanger. So the air goes through these coils, comes out the other side. We don't know the temperature, we're going to find it. The pressure is now reduced to 4.5 bar. It's going to be sent through the second turbine, spins those blades, power output is produced. We need to find what that is. It leaves that turbine with a temperature of 980 kelvins and a reduced pressure again of 1 bar. Now on the opposite side of this heat exchanger, we're going to send air in at a temperature of 1480 kelvins. Pressure is 1.35 bar. Mass flow rate is given. Comes in here, comes out the other side. The temperature has been reduced to 1200. Pressure is now 1 bar. Alright, now notice this pressure is reduced, so pay attention to that. We'll see how that affects the air that goes out and into turbine 2. Alright, so lots of stuff to keep track of there. Let's go ahead and get started. We're going to start on part A first, which is finding T3. So that is finding this temperature right here. Now remember that this is steady state, and in order to really find out much about this temperature, I'm going to need to know mass flow. So we're going to look at turbine 1 first. So let's do turbine 1. Since we're steady state, we know M1 dot has to equal M2 dot. We're going to go back to our regular old control volume energy balance equation for this part. Steady state, so left side is 0. That's going to equal Q dot minus W dot plus M dot, or we can call it M1 dot, times H1 minus H2. Kinetic and potential energy effects are ignored. So let's not even bother writing those down. Let's go ahead and solve for M1 dot. We're going to have W dot over H1 minus H2. Now some of y'all might be wondering, where's Q dot? You didn't put Q dot in there. Well, do you know, can you figure out why I didn't put Q dot? What do you think? If you look up here, it says we're ignoring straight heat transfer. So that's going to make that go away. Okay. So now we're left with this equation. H1 and H2, those can be found in the table. We've got an ideal gas, so you're going to look in table A22. And H1, if you do that, if you look up the temperature 1400, your enthalpy value is going to be 1515.42 kilojoules per kilogram. That's the ideal gas table. H2, you do the same thing. We just now have a temperature of 1100. So that gives you an enthalpy of 1161.07 kilojoules per kilogram. So now we have that, and that gives us the denominator. Do we have W dot? Yep, we do, because that's the power output of the turbine. That's 10,000. So we've already got that. So let's fill all of this in. M1 dot then is going to be 10,000 kilowatts over 1515.42 minus 1161.07. And this is kilojoules per kilogram. There you go. Now you can actually see it. Are our units good here? No, I don't think so. This is mass flow rate, right? We want kilograms per second. We don't have seconds in here. And we've got this kilowatts. So let's do a conversion up here at the top. We're going to do 1 kilojoule per second. Put that over 1 kilowatt. That gets rid of that. And then the kilojoules goes away. Now that gives us 28.22 kilograms per second. So that's our mass flow rate for turbine 1. All right, so mass flow rate of the air going in and coming out. Now that we've gotten here, now we're going to go to our heat exchanger because we want the temperature of the air coming out of this heat exchanger. So for this next part, what we're going to do is we're going to develop our equation for the heat exchanger, the whole thing. So our control volume, or the boundary, would basically be this square around the heat exchanger. So that'll be our next step. So let's put on here, we've got the heat exchanger. This is still steady state. So M1 dot, remember, is M2 dot. And then that's got to be M3 dot, which has to be M4 dot. And then on the bottom side of the heat exchanger, we've got M5 dot, which is going to have to be equal to M6 dot. So now we've got all of that information. Next, we want to write an energy balance equation for the heat exchanger. We're steady state, so we still have 0. That's got to equal Q dot minus W dot plus M2 dot times H2 minus H3 plus M5 dot times H5 minus H6. And just in case you're wondering where these came from, because you might be like, well, where's M3 dot and where's M6 dot? I don't see those. Remember that we've got these relationships here. So this was essentially M2 dot H2 minus M3 dot H3, but M3 dot is M2 dot. So we just made the substitution. All right, so that's why those are missing up here. Now, a couple other things. For a heat exchanger, are we going to be producing power? Nope. Are we going to need power? Nope. So this goes away. Q dot, we going to have that? Not going to have that, because it said to ignore stray heat transfer. So now we get rid of that. Now we're just left with this portion here. So let's go ahead, we're going to fill in the values that we have. So we got 0 equals M2 dot, we found that, it was 28.22 kilograms per second. We're going to multiply by H2, which we found in that last section. So that's 1161.07, that is kilojoules per kilogram. And then subtract H3, which we don't know. And we can't find because we don't have a temperature. So that's got to stay just H3. Next we do M5 dot. That was given in the picture. That was 1200 kilograms per minute. Do we ever leave anything in minutes? No, not usually. So let's convert over to seconds. And then we've got H5 minus H6. We have the temperatures for both of these locations, so you just use the temperature, go to your ideal gas table, and pull out those numbers for H. So at 5, you got 1611.79. 0.6, you got 1277.79. And these are kilojoule per kilogram. So again, that's table A22. All right. Let's double check these units. Thinking they're all pretty good here. Those will all work out. Okay, so that'll look good. Now, notice our only unknown here is H3. All right, so H3, that means we can solve this equation for H3. And if you do that, you get 1398.77 kilojoules per kilogram. Now, you might be wondering, what am I going to do with that? Because this is all we have left. We still don't have a temperature, right? We just have this enthalpy value. That's all we got. Now, what we're going to do then is let's look at this table, A22. so if we look at the table, if you think about it, what we can do is we can find this value, 1398. Let's see if there's any values close to that in this table. Alright, so we had 1398, here's 1372, here's 1395, 1419. So what we're going to have to do is we're going to have to take these two data points and we're going to interpolate to get our temperature. We know our temperature is going to be between 1300 and 1320 though, if we do the calculations correctly. Alright, so we're going to interpolate here. So let's write down the two data points we're going to use. So when T is 1300, enthalpy is 1395.97. When it's 1320, it's 1419.76. So if you interpolate, what you're going to get is T3, and you get 1301.5 kelvins. All right. So that's pretty interesting, right? We were able to find our temperature using two different control volumes and our control volume energy balance equation. Now that took care of part A. Now we have to find the power output of the second turbine. So that'll be part B. So this is finding W dot for turbine 2. Now we need a W dot in an equation. So again, let's go ahead, think of a control volume we could use to find that. And obviously a good choice would be to make the control volume this turbine right here, because it's got air coming in and it's going out. So let's use that as our next control volume. And then we're going to write the control volume energy balance equation again for turbine 2. This is still steady state, so it's still 0 on the left side. Q dot minus W dot plus M4 dot times H3 minus H4. Alright, so now we got that. Can we simplify anything there? Yep. That goes to 0. Now, this is what we're looking for, right? This is the power output for that turbine. So if we can plug in our numbers for all of this, we have the power output. So let's go ahead and solve that equation for W dot and plug the numbers in. M4 dot is going to be 28.22. And then H3 and H4, we can find those values because we have the temperatures for both of those. H3 we actually found right here. So we'll have 1398.77 kilojoules per kilogram. And then H4, you can find that in the table because we have the temperature. So use the temperature of 980, look up that value in A22. You'll get 1023.25. That's kilojoules per kilogram. All right, so again, you can find those in A22. Oh, except for this one. This one we interpolated. But so now we have this. Let's go ahead and let's solve here. So W dot is going to be 10,597.17. The units will be kilojoules per second, because notice kilograms go away. It wanted it to be in units of kilowatts. Now remember, this here is kilowatts. So you could just rewrite it as 10,597.17 kilowatts. So that's your power produced from turbine 2. Perfect. And it's positive, like we would expect if you're sending power out. A few more things to find. We got to do C and then D. So part C, We're looking for the rates of entropy production for turbine 1 and the heat exchanger. Alright, so we're going to find these two rates of entropy production, turbine 1 and the heat exchanger. Now let's look at turbine 1 first. And we need an equation that has sigma dot in it. So our equation we're going to use is that new equation we just developed. That's the one with the sigma q dot over t plus m1 dot s1 minus m2 dot s2 plus sigma cv dot. Alright, so that'll be our equation. Now this term right here, we don't have any heat transfer, so let's get rid of that. That goes away. And now let's look at the rest. We know m1 dot is equal to m2 dot, so let's simplify this equation. We'll say 0 equals m1 dot times s1 minus s2 plus sigma dot cv. Alright, so now we've got that. And we can solve this for sigma dot. So sigma dot is going to be m1 dot times s1 minus s2. And we know, since we have an ideal gas, that we can set that equal to m1 dot times the s degree at T2 minus s degree T1 minus r times the natural log of P2 over P1. And we're going to do this because we weren't told anything about specific heats. All right, we don't know anything about it, so we'll use this equation here because of that reason. So now we just need to plug in values. Okay, so we're going to stick with this second part of the equation. All right, so m1 dot was 28.22 kilograms per second. We're going to multiply that by the values that you get out of table A22. That's the ideal gas table. Alright, so at temperature 2, which temperature 2 is 1100 kelvins, the value you get in the table is 3.07732. That's kilojoules per kilogram Kelvin. We're going to subtract the S value you get at T1. T1 was 1400, so you'll get 3.362. And that's kilojoules per kilogram Kelvin. Then we subtract R, which that's 8.31 over 28.97. It's kilojoules per kilogram Kelvin also, times the natural log of 5 over 20. Alright, so we're almost done with this part. Now you just have to go through and solve. Notice kilograms go away. So that'll go away, and there you go. Now we're going to end up with units of kilojoules per second kelvins. So our rate of entropy production for turbine 1 is going to be 3.1936 kilowatts, because remember, we get kilojoules per second, that's a kilowatt, per Kelvin. So there is your first answer for part C. Now we got to do the same thing for the heat exchanger. Alright, so let's do that next part. Now you're going to come up with your control volume again. So this time you want to look at the whole heat exchanger. So let's put control volume equals the heat exchanger. And if we do that and write out our equation, it's still steady state, so that goes to 0. And we got sigma q dot over t plus m2 dot s2 minus m3 dot s3 plus M5 dot S5 minus M6 dot S6 plus sigma dot for the heat exchanger. Okay, so all we're doing is going through finding the inlets and then the outlets. That's all we're doing there. Now this term goes away because we have no Q dot, and then that's what we're left with. And again, we can replace M3 dot with M2 dot because those are equal. Same thing over here. M6 dot is equal to M5 dot. So let's rewrite it as 0 equals M2 dot times S2 minus S3 plus M5 dot times S5 minus S6 plus sigma dot HE. Alright, so now that we've got that, I gotta get another piece of paper here. Let's move this up. Now we need to plug in our numbers, and then we can get sigma dot. Alright, so let's go ahead and plug these in. Now remember, S2 minus S3, we don't know anything about CP, right? We don't know anything about our specific heat, so we're going to use that S degree value again. And if you look in the ideal gas table, you will see right there that it gives you S degree. So that's your only choice. You have to use that term. So let's rewrite this equation. We're going to have 0 equals 28.22 kilogram per second times this here. Remember, this is going to equal S degree at T2 minus S degree at T3 minus R natural log P3 over P2. So all of this is for that. Then we have the plus M5 dot. That was 1200 kilograms per minute. We don't want to leave that in minutes though. Let's convert it. So divide by 60. And now again, we've got this S5 minus S6. Well, you can't just go to the table and find these. You have to use this same setup here. So we'll do that over here. We'll find the value when T is at 0.5. And then we'll find the S value for T6. And I'm out of room, so let's move down here. Then we'll subtract R times natural log of P6 over P5. Okay, lots of stuff there. Now, so I don't have to rewrite all of this out, I'll just write out what these values are. If you go to the table, look up the temperature of T2 and find S, you will get 3.07732. This one at T3, you're going to get 3.27481. Over here at the T5, I'm kind of out of room. Let's see, let's put it right here. That's going to be 3.42892. And then finally this one is 3.17888. Alright, so that's what you get when you look up all the values in the tables. When you plug all of these things in, what you're going to end up with is sigma dot for your heat exchanger. It's going to be 3.1482 kilowatts per Kelvin. Alright, so now you got your entropy rate right here for your heat exchanger. Alright, so it's a little bit lower than that of the turbine. Now, that's the hard part. So the hard part's done. Now we're on part D. Part D, we were looking to rank the components in order of inefficiency. So for this, we were calculating rates of entropy production. So let's go ahead and look at those. So if we rank them in order of inefficiency, we're going to have turbine 1, which we got 3.1936. So this means, well, actually, let's write out the rest first, and then I'll talk about it. That'll make more sense. For our heat exchanger, let's write out its rate of entropy production. It was 3.1482. And then for the other turbine, its entropy rate production was 2.86499. All right. So now we got that. Now, all of that being said, these are in order of inefficiencies. So remember we wrote down how if it's greater than 0, it's got irreversibilities. So the higher this number is, typically the more irreversibilities it's got. So this is going to be the most inefficient, next inefficient, then the final. Okay. So now there is the final solution for all of the problems. All right, so that was kind of a long one. It had lots of stuff in there, but hopefully you enjoyed it and found it informative. All right, I will see y'all next time.